So thank you very much for the invitation to speak. Thanks to Angela and Miles and Monica. So I want to give an explanation of a project that I've been doing over quite a few years now with Melanie Rupflin. And I've also got some other co-authors here that I've listed. So this is to do with the harmonic map energy and its gradient flow, but it's a little bit different to the ordinary harmonic map flow. So let me try to explain. So this is the basic setup. So also for the ordinary harmonic map problem. So you have a map U. Let me try and a bit confused how to get the annotation. Monica, do you know? Okay, I've lost it.
Yeah, so, me too. Sorry.
Okay. So we have a map from a manifold here, MG, and this can be any closed manifold. For almost the whole talk, it's going to be a surface and a closed surface. So a two-sphere, torus, hygenus surface, something like that. Just briefly, it will be just a circle in a second. So it's going to map into a target, which is a closed Riemannian manifold of whatever dimension. And you can think of it as being a sphere for a moment. And you can also think of this as being embedded in this Euclidean space Rk. Okay, so you can always do that. So the harmonic map energy is just the Dirichlet energy in this setting. So you can define it here, E of u is just half the integral of du squared. Okay, so because we've got k components, we're mapping into Rk, this is just the sum of the ordinary Dirichlet energies of those k components. Okay, critical points are harmonic maps. So what about the harmonic map flow? So this is the starting point of geometric flow theory. So introduced by Eales and Sampson in 1964. So this is the L2 gradient flow for E, this energy. So basically you have some sort of map U and you deform it in order to make the energy drop as quickly as possible. So what's the PDE that is actually governing that? So if we were mapping into just Rk, then the gradient flow for this energy would just be the heat equation. So here we have du by dt equals Laplacian u, which is like the heat equation, but we have to do this projection T that I've marked with a T here. So if you look at the picture, then what's going on is that maybe this surface here is the target N, and we've got a point here, which is an image point u of x. So Laplacian of u is a vector which may not point in the direction of the tangent space of this manifold N. So you just got to project it down so that it does. And that's what I mean by Laplacian u with the T. Okay, so if you actually want to see the PD, let's do it in an explicit situation. So let's say that the target manifold was just a sphere, Sk minus 1. So that's obviously sitting very nicely in Rk. So then to get this projection T, the right thing to do is to add on a term here, u du squared. So you see this nice parabolic equation. It's actually a system. Maybe I should put indices in here. So I is going from 1 to k. And it's got a nice nonlinearity. So that gives you an idea of the equation. Okay, so let's do an example. So for most of the talk, as I say, the domain M is going to be a surface, but let's just for this slide, consider it to be S1, because that gives you a nice example to think about. And for most of the talk, the target you would normally think of as being 3 or higher dimensional, but just here, think of it as being this torus here. Okay, so in the one-dimensional domain situation, then this is a subcritical situation. So the flow will be smooth and it'll exist for all time. So let's say this pink curve here wrapping around the torus is the image of initial data u sub 0. Then the flow will exist for all time and gradually move down here to this limiting curve u infinity. Okay, so it's as good as you could hope, really. So given that fact, then you might hope that if you go up by one dimension of the domain, and M you consider to be a surface, then you might think that the flow will converge nicely to the analog of geodesics one dimension up. So that would be a minimal surface, so that you might hope that the image would be a critical point of the area functional rather than the length functional as it is here. So that's not like to happen in general, because the critical points of this function are harmonic maps. They're not minimal surfaces. So on the other hand, there is one situation where you can expect that maybe something nice works. So actually, if the domain is the two-dimensional sphere, then you can actually prove that if you have a harmonic map, S2 to any target, then in some sense, the image is a minimal surface. So as long as the you're away from points where the differential of the map vanishes. Okay, so we'll come back to this idea in a moment. Okay, so let's go up one dimension again. So dimension of the domain is 2. So this is the critical dimension. So this means several things in this talk, but essentially you have a functional which is invariant under scaling. Okay, so Struve kicked off this theory in 1985 in a very influential paper. And he basically proved that if you give him initial data, let's just take a smooth map from the surface to your target manifold, then there exists a global weak solution from space-time. So this will be a W12 solution, for instance. It'll have finite energy at each time. And this has a very nice regularity theory. So it's going to be smooth, except at finitely many points in space-time. So not just at each time there might be finitely many singularities, but throughout the whole of space-time there are only finitely many singularities. Okay, so the picture of what happens there is very standard, and a lot of people in the audience are doing this sort of thing all the time. But let me quickly, just on this slide, go through what happens. So in this picture here, we have the domain M, or a little bit of it, in fact. And on the right-hand side here, I'm drawing the image of U. So we're working, just imagine we're at one time in this picture, a little bit before the singular time. So this point X is being mapped by U to maybe the top of this picture over here on the right. And what's happening is you're getting concentration of the map. So a very small disk around X is being mapped to quite a large area in the target. And then maybe the rest of this little portion of the domain is being mapped in a nice way to the rest of this image here. Okay, so what you do, of course, in any context in PD theory analysis, geometric analysis, whatever, when you have this sort of blow up property, is that you rescale. So here I've drawn a sort of rescaling. I've sort of blown up this small disk to a larger disk. So you'd be doing this at a sequence of times approaching the singular time. And in the limit, you'd actually have down here on this bottom of this picture, you'd actually be living on the whole of R2, the whole of this sort of tangent space to X here. So if you do it in the right way, and then you can take a limit, and you'll actually end up converging to a critical point, a non-constant harmonic map from the whole of R2 here to the target. So intuitively, it would be mapping to this sort of region here on the right. Okay, so now we're going to use the criticality of this equation, and that manifests itself in that we can change the domain conformally. We can just multiply the metric by some positive function, and it won't change the energy, so it won't change the critical points. So in particular, R2 is, as far as harmonic maps are concerned, is just the same as S2 minus a point. You know, just stereographic projection will give you a formal map from one to the other. And then a little bit of analysis. Sachs-Uhlenbeck removable singularity theorem says that once you have a harmonic map on this sphere minus a point, then you can extend it across this puncture here, and you end up with a harmonic map on the whole of S2. So this is what we mean by a bubble, this harmonic map. So typically it would be mapping to, whoops, just this top bit of the image here. Okay, so that's gives you immediately a nice application. So if we're in a situation where the target doesn't have any, when there aren't any harmonic maps from S2 to the target, and there are many situations like that, you know, maybe we're mapping our initial data into a region of the target which admits a convex function. So that would be an instance of where that was true. Or you maybe have negative curvature, for instance, or many other situations. So then what you deduce from this theory is that the flow then will actually be smooth for all time and will converge or subconverge at infinity to a harmonic map. So it's very nice how this works out. You've got all the PD theory in the top, and it gives you this geometric picture, and then it gives you a very nice geometric characterization of singularities. Okay. So now let's change the viewpoint a little bit. So instead of thinking of the harmonic map energy as an energy which acts on maps alone, we're going to consider it as a functional which acts on pairs of maps U and metrics G. So G is the metric on the domain surface. Okay, so from now on we're only doing domain surfaces. Okay, so let's suppose that we have a critical point now of this functional viewed in this way. So one consequence of that is that for fixed G, I can vary U and I'll be critical. So that basically means that I've got U being a harmonic map. But something more is true, of course. So if I fix U and vary G, then I'm also critical, which I'm not generally for a harmonic map. So that gives me another condition. So what is that? So that will tell us that actually U is a conformal map, okay, or weakly conformal. So in other words, the differential can vanish. So, you know, rephrased a little bit, you can always reduce the energy, even if you've got a harmonic map, to first order if U is not a conformal map, okay? So a nice fact, not hard to see, in fact, though let me not dwell on that, is that if you have a map which is harmonic and conformal, then the image of that map is actually a minimal surface. So such special harmonic maps give you minimal surfaces. So they give you images that are critical points for the area functional. Okay, so this is a fact which has been exploited a lot in the past. So I've just written down here the works around the same time as Shane Yao and Sachs-Uhlenbeck, but long before that, this sort of general idea was being exploited one way or another. Okay, so here's the idea. Maybe if you do a gradient flow of energy where you don't just vary the map U, but you also vary the metric G, then instead of finding harmonic maps, you might actually find minimal surfaces. So that's the starting point of this theory with Melny Rupflin. Okay, so you could write down the L2 gradient flow equations, and you get a not too complicated set of equations, but the actual analysis of those is not actually so great. So in particular, there's no mechanism when you do a gradient flow of this energy for creating smoothing effect in G. Okay, it's smoothing U, it's a nice parabolic equation in U, but it's not smoothing G. And also this goal of trying to find a minimal surface, so essentially taking an arbitrary initial map U0 and then trying to deform it to a minimal surface, it's just too strong. So typically there is no minimal surface that you can deform an initial map to. Okay, so let me just go sideways a little bit. Whenever I say minimal surface in this talk, though you needn't particularly worry about it, I really mean a minimal immersion. So it could fold back and meet itself. And if we're not quite conformal, if we're weakly conformal, there might be isolated points where we get some branching. Okay, so here's the basic idea, and maybe it's a bit too strong. Okay, so we're going to solve that by the following simplification. We're again going to use the criticality of the equation. So we're going to use the fact the energy is conformally invariant. So this is really a two-dimensional fact. So I've written it out. So the energy of UG is the same as the energy of U rho G, where rho is any positive function. Okay. And I've reminded you just here of the energy. Okay, so we're going to use this fact in the following way. We're going to choose a good rho and replace G by rho G. So here's a standard fact from a very long time ago, maybe 100 years ago. So if you give me any metric on a surface, you can always conformally deform it to a rho G, which is a metric of constant curvature. So we're working on a closed surface here. Actually, always let's just take a closed oriented surface. So think S2, T2, surface of genus 2, 3, 4, etc. So if you're topologically S2, then you can always deform it so that it's a round sphere. If you're a torus, then you can always deform it so that it's flat. That's particularly easy to do. A very simple equation does that for you. And in this one case, then you can do an extra scaling without changing the curvature. So you may as well normalize so the area is 1. If you have higher genus, so more holes than a torus, then you take your curvature to be -1. So this is constrained by the Gauss-Bonnet theorem, essentially integration by parts. Okay, so, or divergence theorem. So in that situation where you have curvature -1, then that's known as a hyperbolic surface. Okay, so what we're going to do is we're going to constrain our metrics G to have constant curvature 1, 0, or -1. And we're only going to move amongst metrics with that condition. Okay, so I want to tell you a little bit about the situation where the curvature is -1. And that's, in some sense, the most delicate situation. In most senses, it's the most delicate situation. So I'm going to give you a one-slide crash course in hyperbolic surfaces aimed at people coming from a PD background. So this is sort of pictures, but I can very quickly give you a couple of very key ideas. So we're talking about surfaces of 2 or more holes. Okay? So the idea is you can actually deform your metric in a finite dimensional space of directions and remain hyperbolic. Okay, so maybe I should just say, whenever I'm talking about surfaces, I'm not talking about surfaces in R3. Okay, I'm talking about them intrinsically. So you could never have a closed surface in R3 of negative curvature. You'd have positive curvature at the edge. So I'm only thinking, this is just a schematic picture. Okay, so where does this 6 times genus -1 dimensional space of directions I can move come from? So there's a very nice picture behind that. So the picture is following. So these closed hyperbolic surfaces can be constructed out of simple building blocks. They're normally called pairs of pants. So here's the key fact, which has a really very elegant proof. If you give me any 3 positive numbers, L1, L2, L3, then there's a unique hyperbolic surface which looks like this. So it has that topology. It has 3 ends, and the ends are geodesics. Okay, each of these geodesics, and their lengths are L1, L2, L3. So that is the one key fact that you need to understand this whole subject. Now, if one of the lengths goes small, like I've sort of started making L3 small here, then it becomes longer here. So this is all in a very precise way. I could write down the metric in a neighborhood of one of these, though not very easily globally. Okay, so given that fact, let me just shift the screen up a little bit so I can squeeze some more stuff in underneath. So we can use these pairs of pants we can use them like little building blocks. So just imagine some sort of kid's toy, and I can sort of piece them together. So let's say I had two of these pairs of pence that shared a common length L3. Then I can just take the two and just glue them together along that L3. And the metric here is completely explicit. So the join here will be completely smooth, completely analytic, in fact. Okay, so let's do one example. So one way of constructing a two-holed surface, you could pick one pair of pence with lengths, two of them equal to A, one of them equal to C. And then for the other one, take two of the lengths equal to B, the other equal to C again, and then glue them together. And you get a picture here which is no longer geometrically correct, but it sort of shows you what's going on. So this is, in the middle here, you've got where the L3 is. And then this left-hand part here is supposed to be one of these pairs of pence over here. But I've had to sort of manipulate the geometry so they're sort of glued together. So, you know, just imagine this picture up here with these two lengths the same. And as you move off here, you go into sort of hyperspace and come in over here. Now, when you do that, go into this sort of wormhole and come back over the other side, you have a choice of sort of rotation of how you glue those together. So that gives you some extra parameters. So in this situation, I'd have three sort of rotation parameters and three parameters A, B, and C. So we've got six dimensions. That's the right number of dimensions. So I've basically explained to you every way, geometrically, every way I could vary this hyperbolic surface at the bottom. I can manipulate the length A, C, B, and I can just gradually rotate these joins there, and there. Okay, so that's a geometric picture. It's absolutely not enough to do PDE theory. Okay, so this is actually a somewhat subtle point. So the point is, what I've described here is all the different possible sort of shapes of these surfaces, but when I do that, I don't really have a good sort of reference from one of these hyperbolic surfaces to the deformed one. So let me give you an example. If I'm standing on this hyperbolic surface and you manipulate the A, C, and B and what have you, where am I now standing? Am I standing just a bit to the right or a bit to the left? Or, you know, there is no such thing as staying still. Okay, so of course this is a massive problem for PDE theory. If I'm solving a PDE on this surface, okay, this issue, by the way, is going to come up whenever you solve a PDE on an evolving surface, not just if you're taking hyperbolic surfaces. Okay, so if I'm solving some parabolic PDE, for instance, on this surface, then I really need to know where one point at time t corresponds to at time t plus epsilon. Okay, so you know, just solve the diffusion equation on this surface, for instance. You've sort of got a problem that you want to sort of add a transport term, but you don't really know what to add. Okay, so let's resolve that in the next slide. So to formulate these PDEs, then we're going to have to take a slightly more sort of analysis approach. So in these boxes here, on the left here, I've got the directions that we could move the metric G, keeping us our hyperbolic metric. So this space here, this infinite dimensional space, actually decomposes in a nice way. So it decomposes into an infinite dimensional space, which is just reparameterizations. So you're just sort of pulling back by, you know, you're just changing coordinates infinitesimally. So you're just pulling back by the identity perturbed a little bit. So it decomposes into that plus finite dimensional space, which is corresponding to these variations that I was considering before. Okay, so in different language, I can write the tangent space. So MC here is going to be the space of constant curvature C metrics. Okay, so this left-hand side, the tangent space at G, that's all the directions I could push my metric G, so I remained a hyperbolic metric. So this is the sort of geometer's way of writing all the directions which don't really change the geometry. They wouldn't change the lengths of any geodesics and what have you. And H is the space, this finite dimensional space of genuine changes. So from a PD point of view, you can characterize those. These are all very regular. They're trace-free, divergence-free tensors. So this, by the way, this is very much like decomposing a vector field into a sum of a gradient and a divergence-free part. Okay, it's just exactly the same argument. Okay, so so if we want to formulate a PDE for our metric G, then we can solve the problem on the last slide by declaring we're only going to move it in the direction, in one of these directions in H, one of these 6 gamma minus 1 dimensional space of directions. Okay, those are so-called horizontal directions. Okay, so if I move everything up on the slide, I can squeeze in the actual system of PDEs. So the gradient flow for the energy turns out then to be this system of PDEs. So you've basically got the harmonic map flow, this nice parabolic equation for U. And then G is like a gradient flow. So if I just had this gradient E, it would just be a gradient flow, but then I project onto H. Okay, so that not only keeps me hyperbolic, but it solves this problem of getting rid of this sort of infinite dimensional space of sort of nonsense directions there. So let me tell you what this gradient E is here in practice, so you can work it out in coordinates. Probably the simplest way of doing that is to take spatial coordinates locally, so-called isothermal coordinates, but just nice coordinates locally, so that du by dx is orthogonal to du by dy. So just rotate the coordinates until that's true. And then you could write this gradient of the energy as this expression here. So this is like dx tensor dx, and this is dy tensor dy. So if you're not used to the notation, it's basically saying you're stretching in the x direction by at this rate, and you're squashing in the y direction at minus that, basically. Okay, so that's sort of changing the idea of what's conformal. Okay, so does it work? So we're trying to use this flow to deform initial data, so an initial map U0, an initial metric G0, to a critical point of the energy. Let's call it U bar G bar. And in that case, if we achieved it, then we get a minimal immersion. Okay, so reality is a little bit more difficult, and anyone doing nonlinear PD theory can imagine why. It's because we get some singularities, for good geometric reasons, in fact. So the first way that we can get a singularity is extremely familiar. So bubbling may occur. It's just the same picture I had on maybe slide 3 or whatever it was in the talk. So energy can concentrate. You have to rescale where it concentrates to capture some limiting harmonic map. And then you can phrase that as a harmonic map from S2. That would be your bubble. Okay, so from Struve's work, then you already know basically what to do in order to restart the flow. You can do a full analysis of this sort of thing. In particular, you can prove a so-called no loss of energy result. That's sort of standard thing to do in this sort of game. In I guess in the context of harmonic map flow, it was proved by Qing and Tian. And that's basically saying that the amount that the energy will drop down at the singular time is exactly equal to the energy of your bubble, or maybe you get more than one bubble. Let's not worry about that. But then it would be the sum of the energies of the bubble. So that's all very familiar, but you can also now get a different type of singularity. So the domain metric may degenerate. So here's a picture of a possible, in this case, genus 4 domain surface. And it might be, and it certainly is the case in general, that in the course of trying to reduce the energy, then you might have a geodesic, so right at the center here, there's a little tiny geodesic going around, you might have a geodesic whose length is getting smaller and smaller and smaller and converging to zero. As I said, when that happens, then everything stretches out, as indicated by these arrows. Okay, so this geodesic may actually go to zero. Okay, in which case it becomes completely stretched. So that's what I'm going to draw on the next picture. So that's the old picture just repeated. So let's imagine I'm standing over here on the left and someone else is standing over here on the right. If I look over this sort of range, then as the geodesic in the middle has its length going to zero, then everything is converging nicely. The surface is converging nicely over here. And for someone standing over here, then everything in this sort of region is converging nicely. But this has length going to infinity. So what happens in the limit will actually get convergence to non-compact surfaces. So this will now actually have unbounded diameter. So I've drawn them still the same distance on the page, but now someone standing over here is now infinitely far away from someone standing over there. Okay, so this is sort of bubbling in a sense. We'll see something that looks more like bubbling in a second, and maybe it looks a little bad, and maybe you're not sure what to do now with each of these two surfaces that you've got. Well, luckily, the metric on this so-called hyperbolic cusp that we'll develop here is completely well understood. And you can just change the metric conformally so that the surfaces now look like this and like that on the right. So I've drawn a little puncture, a little cross here represents a point removed, which corresponds to the point at infinity here and the point at infinity here. Okay, let's call them sigma 1, sigma 2. Okay, so this sort of process could, in theory, happen at finite time, and it can certainly happen at infinite time. So we have to decide what to do in both of these situations. Okay, so I'm getting a question on the chat. Oh, so Stephen's asking about the comparison with the neck pinching for Ricci flow. Let me answer that at the end. So actually, they're not that similar, I would say, except as in all nonlinear PDE, you can have sort of blow up degeneration, this sort of thing, and they have that in common. But from a PD point of view, they're actually very different. Okay, so this sort of splitting up here can, in theory, happen at finite time. Certainly happen at infinite time. Okay. So if the metric degenerates at finite time, then we can actually continue the flow as multiple flows. Let me go back one slide. So you can actually, of course, you've got a map living on this surface, and you can actually find a limit on each of these. That's going to be a W12 function. And doesn't satisfy any PD at that time, but W12 function obviously extends nicely across one puncture here, and then you can just continue the flow. And the same over here. So then you'll have two solutions coming. And so you could have this happen finitely many times, and you might have a number of different solutions. Okay, but it can only happen finitely many times. Now, this picture could also hold at infinite time. If that happens, then you have to work a bit to get convergence of the map U to a map now on this surface here and on this surface here. And what you can do is you can argue that these limits are actually going to be harmonic. So that will extend nicely across these punctures using Sachs-Uhlenbeck. And then you have to argue that these harmonic maps are actually conformal. So you'll end up with a branch minimal immersion. So this is the domain, of course, I'm drawing here. You'll end up with a minimal surface from here to the target and from here to the target. So of course, this idea that you might take initial data and just deform it to a minimal surface was too naive. So here you can see that you're getting a collection of minimal surfaces. Now, in this process, you get an interesting new type of bubbling or blow up that can happen. So this is explained in this picture here. So here's our surface again. And this center of the surface, of course, is shrinking and stretching. So as it gets smaller and smaller and smaller, the geodesic gets smaller and smaller and smaller, and it gets longer and longer and longer. Then geometrically, it looks more and more and more like a longer and longer and longer bit of a cylinder, S1 cross R, okay? So this is very similar to bubbling, where you have everything concentrating at a disk and you blow up to R2. Here you're blowing up to a cylinder, okay? So if you do it in the right way, then you'll actually be able to get convergence of your map to a map on this whole cylinder. This is very similar to bubbling. You get convergence to a harmonic map on the whole of R2. So we've managed to extract a harmonic map from this whole cylinder. And then we again then appeal to the criticality of the PDE. So an infinite cylinder, if I can formally change the metric, I can end up with a two-dimensional round sphere with 2 points removed. Of course, that point is corresponding to the point at infinity on one side of the cylinder, and this point is corresponding to the point at infinity on that side of the cylinder. Okay? So we managed again to extract a harmonic map from a punctured sphere, and Sachs-Uhlenbeck once more allows you to remove the singularities and you get a harmonic map on the whole sphere. So you get a different type of bubble. So you can have multiple bubbles and various other behavior going on. I'll come back to this slide in a second. So let's give a sort of heuristic idea of what you end up proving with all these arguments. So this is a combination of results, all proved with Melanie. Everything I'm talking about is joint with Melanie, and some of it's joint with Miao Miao Zhu, and some of it's joint with Tobias Huxell. And the theory basically says the following: if you give me initial data, so an initial map U0 and an initial metric G0, then you can find a global weak solution. So that's a little bit more complicated than Struve's weak solution, because your domain is not fixed, right? It's changing like I've been describing. You have smoothness except for the blow-ups that I've described above. And then the flow is decomposing this initial data into a finite connection of minimal immersions. So if I just go back briefly to this slide. So here we've got a minimal immersion on sigma 1 and on sigma 2, if this is happening at infinite time. But we've also got all these bubbles. And of course, those are harmonic maps from S2. So they themselves are also minimal immersions, okay? So I have to take all of those different possible minimal immersions living on surfaces of whatever genus. And if I add up their energy, then I exactly get the limit energy of this flow. So that's a no loss of energy result. Okay, so if I just go back to the last slide, this actually ends up being a little bit subtle for the following reason. If I have energy that's sort of collecting on the middle of this long cylinder, then I'm going to capture it by doing this blow-up procedure. And if I've got energy which is sort of hanging around on one side of the surface, then I'm going to capture it as a harmonic map from sigma 1 or from sigma 2. But there's a nightmare scenario, which is that you have energy which is sort of starting off here and then it's drifting off down this long stretching bit of the surface, but it's not going so far that it ends up in the center where everything is becoming harmonic. I'm talking about a finite time singularity here. Okay, so in the center, sort of a PD, proving the right estimates tells you that the size of this has to be so small compared with the time left to the singular time that when you rescale, everything becomes harmonic and you extract something harmonic in a limit. If you add energy sort of collecting sort of further and further out on the surface, but not far enough out that it became harmonic, then you'd be really in trouble. You'd actually lose energy. So a lot of the work in proving this result is to show that that sort of bad energy does not actually cause any trouble. And the proof is somehow that if you want this energy to drift down the collar, it takes a certain amount of energy to move energy, and you just don't have enough. Okay, so this is a fairly vague statement. Let me try and explain what it actually means. So here's a theorem. So this is probably the easiest theorem that you can prove, even though it's a little bit long. It's actually not too hard to prove. So let me go through it relatively quickly so I don't run out of time. So let's suppose we're in the nice situation that none of this blow up happened, so that I can explain things more easily. So let's say I have a nice smooth solution. Okay, so then I can find a sequence of times going to infinity, so that at those times I get convergence. But what does that convergence actually mean? So I have to take a sequence of reparameterization, so diffeomorphisms, Fi, and then if I just jump down to the conclusions, then if I pull back the metric, so basically if I change my viewpoint by those diffeomorphisms, then the metrics at times ti will converge, and they'll converge to g bar, constant curvature metric. Okay, and also if I use the same Fi's to reparameterize the maps, then that sequence of maps will also converge. Okay, so after reparameterizing, then I'll get convergence, and you show that the limiting map, this U bar, is actually a minimal immersion. Okay, so the most obvious question that everyone asked when we started working on this subject is, do you need the diffeomorphisms? So if I go back one slide, maybe if I don't pull back by anything, maybe just the flow at these times ti will just converge. Maybe the g ti's will converge, and maybe the u ti's will converge. So actually for a while we were a bit puzzled by this point, and we couldn't really see a mechanism why something as simple as a gradient flow would actually do, you know, why it would actually require these Fi's, and yet the proof did seem to require them. Okay, so the first thing of the new results I want to tell you about is actually we managed to prove, joint with Melanie and James Cohort, we managed to prove that you do need these Fi's. So basically there exists a completely smooth flow, doesn't have any degeneration at infinite time, no bubbling, no anything. So you can analyze it with the last theorem, so you get convergence at a sequence of times ti, but you really need these Fi's. So the Fi's get worse and worse and worse as I goes to infinity. They have to sort of do more sort of manipulation in order to make everything converge. And in this example, you can even choose different sequence of times ti and si going to infinity, so you get different minimal immersions. So you're getting some sort of widening behavior, which you can get in the harmonic map flow as well. So luckily, it's not always like that. So here's, I want to contrast that with a theorem in the spirit of Alois Sewicz and Leon Simon's work. So this is another theorem with Malny and James. So if you impose, and this is a very popular extra hypothesis in this game, if you impose real analyticity of the target, so you can easily achieve that by just small perturbation. If you have a nice smooth solution like before, then you can find a nice sequence of times going, so if you can find a sequence of times where the gradient of the energy is going to zero, so that's totally easy. But so that then allows you to do a basic bubbling analysis. If when you do that, you don't have any bubbling, so that's hypothesis 2. So it's just a cheap way of forcing there to be no bubbling, is to say the derivative of the map U doesn't blow up. If you don't have this degeneration of geodesics lengths going to 0, then the theorem says not only do you not need any FIs, not only do you get convergence without, but you don't even need the TIs. So there's no problem about someone taking one sequence of T times TI going to infinity, and another person taking another sequence and getting a different minimal immersion. So, so that's basically as good a sort of uniqueness result, a uniqueness of blowups result as you could hope in this particular situation. And that sort of result actually is potentially important for application. So, you know, if you're trying to take a family of maps and you're trying to deform them together to a family of critical points of your functional, then this sort of result is required. So let me, I'm run out of time, so let me in 20 seconds just add some open questions. So trying to prove a result of this form where you don't assume that there's no bubbling, that you don't assume that there's no blow up, that's a big problem. So generally, the topic of Loyer-Sawicz-Simon estimates, if you know what they are, when you do allow singularities, it's actually a major topic. So this whole topic actually started in the 90s in the context of the harmonic map flow, I would say. And there's quite a lot of work on that for other equations now. And maybe a final open question would be, can you actually have finite time degeneration of the domain surface? You can definitely have it at infinite time. Okay, so I'm out of time, so I'm going to stop there. Thank you very much.